Hello and welcome back, guys. This is Coach Williams, Mr. Williams, if you will. Today we're going to be looking at Unit 3's Embedded Assessment Number 1. A reminder, these embedded assessments are designed basically to give you a chance to review or go over the stuff from the previous sections. So this video is kind of just a real quick going over it, but what I wanted to do is give you a chance in case maybe you got confused going through the embedded assessment. What I'll do for each question is I'll give you kind of the background information that you need. And then I'll go through kind of the solution to the question, so that way maybe if you were stuck on number 1, once I go through the background information, just pause the video, work number 1, and then check your answers, all right? Same things with 2 and 3 to make sure we're kind of all on the same page. So first question, what we're looking at here is we have somebody that has a computer monitor, and the story that they're telling us is that they want to buy a new computer monitor, but they want it to be similar to the one they have, meaning same ratio as far as height to width, okay? And so the computer monitor that they have, they give us on a graph, and the original computer monitor is 9 by 12. And so I'm going to list that up here as 9 by 12. And they want one that's similar. And by similar, we're talking height to width. So what we're looking for is an equivalent fraction. Okay. Keep in mind, for equivalent fractions, it means that they would reduce to the same thing. So we want to know which one of the 3 monitors they have a choice of, Model 1, Model 2, or Model 3, are going to reduce to the same fraction as this. So let's start by reducing this. 9 over 12. Hopefully you know that's divisible by 3 and that's divisible by 3, so we would get 3 over 4, okay? And 3 over 4 would be a comparison of the height versus the width, okay? And so that's what we're looking for. In order to get a similar figure, we need one that reduced to 3 over 4, okay? And then another thing you're going to need for number 1 is the idea of a scale factor. So with a scale factor, what you're asking yourself is, what do you multiply the original by to get to the new value, all right? And the way you're going to do that is you're going to list, I would take just the height to keep it simple so it's not stressful. I would take that 9 and I would ask myself, what do I multiply the 9 by? I'm going to put a k, so what am I multiplying by? A lot of times k is used for scale factor. And I'm going to say, what do I multiply 9 by in order to get the new value? Now, we don't know what that new value is yet, but once you have it for the new height, that's the number you would put there, okay? So now is where you want to pause the video and go to number 1. Give you a couple minutes and then come back and restart the video and we'll work through the answer, okay? Bye. All right, welcome back. So here we are. We're going to go through the measurements that they give us for the 3 different monitors that they have there. The first monitor, monitor number 1, measurements is 12 by 16. And so I'm going to match what I did with the first one. I'm going to put height over width. For the next one, it's 16 over 20. So monitor number 2, and we'll kind of just do like this. Monitor number 2 is going to be 16 over 20. And monitor number 3 is going to be 15 over 15. Hopefully you can see that there on page 273 in the PDF file, okay? So our question was, which one of these are similar? And remember, similar means they would have the same ratio. The side lengths would equal the same ratio or would reduce to the same fraction. So 3/4, that's what we're looking for here. So let's reduce these. Well, 15 over 15, this reduces to just 1 over 1 or just 1. So that's obviously not the answer. 16 over 20 is going to be 4 over 5. It's very, very close, okay? 0.8 versus a 0.75. So it's very close, but not the same here. Notice this one, 12 over 16, I saved the best for last. 3 over 4. So this is a similar monitor, okay? Now what we talked about before is the idea of scale factor. I'm going to take my height, my 9K, and I'm going to set it equal to my height in my new monitor, which is 12. And so the question about the scale factor is asking, hey, what do I multiply 9 by to get 12? And you get that pretty easily by simply solving for K. And you're going to get K equals 4 over 3. That is going to be your scale factor, okay? Hopefully that helps. Hopefully that makes sense. Okay, question number 2. Question number 2, we're still talking about the monitors, only this time we're talking about transformations. And what they're going to want us to do is actually describe a transformation that maps the original monitor to the new monitor on the graph that they're given there. I'm erasing this a little bit because I wanted to take a moment here and talk about transformations. You're going to need to know transformation notation in order to do this problem correctly. And so I wanted to review the transformation notation, all right? This first one, this is a translation. This is telling you how far left or right. So this is going to be left or right. Remember, right is positive, left is negative. And this one is going to be up or down. So up or down, down being negative, okay? So that's your transformation notation for a translation. For a reflection, reflection is going to be lowercase r, and we're simply going to put y equals 0, which might happen to be the x-axis, yeah? So if you're reflecting over the x-axis, maybe this is x equals 0, maybe this is y equals 2/3 x plus 3. Whatever line you're reflecting over, wherever you're folding that paper at, that's the line you're going to write there, and then you're going to fold everything over that line. This notation is for a rotation. I put 0 here, not 0, sorry. I put O here, stands for origin, all right? So that means I'm rotating about the origin, but this could be any point. So it could have been rotating around the point 2, 3, and we're rotating negative 45 degrees, okay? Remember, negative is going this direction, whereas a positive 90 is going this direction. Positive is counterclockwise, negative is clockwise, all right? So hopefully that helps with the rotation. And then this last one is dilation, meaning that we're going to shrink something or enlarge it, okay? So the shape is going to stay similar. All the angles are going to stay the same, but the side lengths are going to change. And so this is going to be the center of dilation, and this is going to be your scale factor. So I guess we could label this would be our center of rotation, and this would be direction. Okay, so I wanted to take a minute because I know transformations can be a little tricky. The other thing to remember is that if you're doing a combination of transformations, okay, if you're doing more than one transformation, what you're going to do is you're going to list your first transformation. Let's say you wanted to do a translation 2 to the right and down 3, and then you wanted to dilate it. This is the way your symbolism would work. And so let's say we dilate around the origin and we're going to double everything. So this is what your notation would look like. This would say translate first, do this first. Then do this. That's how the notation works, okay? So with an understanding how the rotation works, I want you to take just a minute, look at number 2, and give me the transformation that would turn her original monitor into her new monitor on the graph. Now keep in mind there's not going to be one magic answer. I'm going to give you what I think is probably the most common answer, but it's not necessarily the only answer that would work. And go. Pause the video, do number 2. All right, welcome back. We're going to erase this because you don't need this anymore, and we're simply going to write our answer. So for number 2, if you look, we know that the monitor has been scaled up, right? She bought a bigger monitor. So the first thing I'm going to do is dilate it, and I'm going to do it around the origin. So I'm going to put the origin, and then I'm going to use my scale factor right here. Remember that I solved for number 1? So my scale factor is 4/3, or 1 1/3. I'm going to do my dilation first. That's going to keep my bottom corner, my A, is going to stay right where it is. It's not going to move off the origin. I like that because then all I got to do is look at what is the shift on A, okay? And it looks like A is going to move from 0 to 0. We're going to translate it, and it's going to go 14 over and 6 up. There is the transformation that works, okay? Hopefully that makes sense. Hopefully everybody's good with that. There's a combination of transformations that gets us from the original monitor to the final monitor, okay? Now we're going to go to the back of the page. Back of the page, we start talking about diagonals of the monitors, which if you didn't know this, diagonal is actually how they measure monitors and or TVs. So if you buy a 50-inch TV, for example, all TVs nowadays are 16 by 9. That's kind of the widescreen ratio. So this is 16 wide and 9 high, okay? So for a 50-inch TV, the 50 inch is not actually the width, the 50 inches is the diagonal. And so by putting 9x and 16x, knowing that that's going to be the ratio, you could actually solve for the height and width of a 50-inch TV. Or 60 or 70 or 80, however big you want to go, you can get the approximate dimensions. Obviously, they might add an inch for a speaker or something, but you can get the screen dimensions, okay? So with that in mind, that's what we're talking about. And what they're asking about is how do you prove that the two monitors are similar given those two triangles? And so what we're going to do is remember, hey, this embedded assessment is going over the stuff that was in the prior unit. And in the prior unit, we did triangle similarity criterion. Triangle similarity criterion. Very similar to congruence criterion. However, with the similarity criterion, all we're looking at is, hey, what makes these two similar? And these were our 3 shortcuts. We could do angle, angle. If you had 2 triangles with 2 matching angles, the triangles were similar, guaranteed, no matter what. if you had two triangles where all the sides were proportional. So maybe one triangle was 3, 4, 5, and the other triangle was double that. Instead of 3, 4, 5, it was 6, 8, 10. Because those fractions would be equivalent to each other, those two triangles were equal. And then the last one is that if you had two sides of one triangle that were proportional to two sides of another triangle, and the angle included between them, the angle between them was the same, those two triangles are congruent, okay? So what number 3 is asking you to do is, hey, look at that picture, figure out how could you justify those two triangles are similar. Well, notice what do they give us? Yeah, they're right angles. They give us the right angles, so they give us one angle. So we could use this, given that we have the right angle, so this is option 1. We could also use this one. Both of these would work, okay? And the way you're gonna do that is you're gonna show that things are similar. My suggestion is, given the two triangles that you have there, go ahead and give the corners letters. And so maybe you call this A, B, C, and maybe for the smaller triangle, no reason in particular, but I'm gonna call it X, Y, Z. And so what you would do is you would show things like, oh, well, it turns out that AB versus BC is equal to XY versus YZ. Okay? And that's kind of how you would want to get started. I know I didn't pause for you to work this one. I just wanted to kind of give you an idea. And from there, I'm going to let you kind of expand upon it and choose which direction you're going to go. Remembering the angle in between them is the same, or you could talk about the hypotenuse as well, since they're right triangles. The hypotenuses are going to be similar to each other as well. That's all I have for the embedded assessment for embedded assessment number 1 from Unit 3, guys. Pages 273, and I hope to see you again in the future. Thank you.